First lecture was about analog of Ginzburg-Landau functional for spin glass, really for infinite range model where each spin is coupled to all other spins, which is not realistic at all. Let's make it a bit more realistic and assume that each spin is coupled to a large over finite number of other spins. And try to describe spin glass transition in a three-dimensional space. Basically, I follow the results we obtained with Lev long ago. You will see that even qualitatively, the picture which I will describe depends quite a lot on some subtle properties of wave functions of a three-dimensional Anderson localization transition. These properties are not all known. Many properties of this transition are well studied, but not everything. What? Not everything. And some of this, so you will see that there is a quite big domain of possible activity for people who know how to diagonalize matrices, how to analyze properties of eigenfunctions, and so on. It will be quite important to relate these purely, if you wish, mathematical properties of wave functions to some deep physical phenomena related to a spin glass transition. So let's try to go. The first line gives you free energy as function of average magnetizations on sides I, and the derivation of this expression was present in the morning. Now, how we can use this expansion? First of all, we're interested to the region close to transition temperature. Actually, at this lecture, I will discuss what's going on above transition temperature. So it will be no really frozen magnetizations, but there will be some modes of fluctuating magnetization which are especially slow. Like, for example, in a ferromagnet, if you are close to transition temperature, then a uniform magnetization fluctuates, and when you approach transition temperature, it fluctuates slower and slower. The same refers to these modes which I'm describing here. Local magnetization, Mi, can be expanded over spectrum. This is a spectral expansion where psi lambda are eigenfunctions of my matrix J. And A lambda are the corresponding amplitudes. Now, about the properties of these wave functions and spectrum. If number of neighbors Z goes to infinity, then the spectrum is standard semicircle. We will consider a bit different situation when Z is large but finite, so it will be semicircle in the main part of spectrum, but not everywhere. I will show it. Then my magnetization can be represented in such a way. Psi naught is a wave function which corresponds to the largest eigenvalue, I mean largest in this z to infinity limit, with some amplitude plus all other. All other contribution comes from other modes here. Then after I use for M this representation, my free energy is given in such a form. Question? No. And I can fix value of A naught, minimize over all other amplitudes, and I will come to this expression. So you see there is some repetition of the morning. I come to this expression. Now let's go further.
What is G and J again? Sorry.
G, it is a green function. It is a green function which just a spectral representation with this psi other than psi naught.
Okay, you're integrating that.
Yes. So still using this infinite z limit, I I also use orthogonality between green function and psi naught, which allows me to derive this equation for free energy as function of the amplitude of my main mode A naught. Now let's start to generalize for finite large Z.
Why there is a singularity in that integral at t equal to 2 plus tau squared?
Say it again.
So the integral that defines the green function at t equal to 2 plus tau squared as a pole.
Yes, but E is bounded in the semicircle, so it never goes to singularity. But now it will. Now we generalize to finite Z. We just assume that variance of coupling is some function of distance between points. Here C is a concentration of our spins in real space, and the mean square strength of the coupling is given by this integral. But you can define effective coordination number or interaction radius, say. So you need to take this integral with k of r multiplied by r squared. Because it is 3D space, you calculate this thing and you assume it is large, but finite in the limit of large system. Simply speaking, each spin interacts with 10, 20, 30, large number of other spins.
It could also be a fast power. I mean, right?
What?
Could be a power law decaying function.
Yes, depending on which power, it could be either finite or it will diverge. Yes. So what kind of function it is, it does not matter, just the integral is some number and this integral is also some number. Now, for infinite Z, it was a semicircle with sharp h at 2. When Z is finite, the most part of the spectrum is the same. But the important difference is that you get localized tails. that there are eigenstates with E larger than 2, density of these eigenstates is low. It decays exponentially. Here, epsilon is E minus 2. So there is a characteristic scale which is epsilon naught, which is related to the coordination number. This characteristic scale is z to power minus 4 over 3. And at larger E, there is a tail of localized states like Lifshitz tail in a Yoshi.
Is described by an instanton?
Yes. Yes, it can be described by instantons. And you can even see these instantons on the next slide. In order to calculate density of states for this problem, we can use either replica functional approach or a supersymmetric functional approach. Anyhow, you deal with some Q, matrix Q. Density of states is given by an integral over this matrix with the action of such a form. Then this action comes due to Hubbard-Startonovich transformation. So you have this kernel k minus 1, and this k minus 1 is equivalent to such expansion, delta function and Laplacian. Then the saddle point approximation for Q matrix is trivial. It gives you the solution which has imaginary path in the region of.
It's okay. Go on. It's okay.
Don't worry. Don't worry. Not something happened?
No, you may continue. That's okay.
Wait a moment.
No
Is
need.
it still entire piece?
Yes.
For saddle point approximation, give you a solution for Q. Q is basically a local green function. So in the then modulus of E is less than 2, it has this imaginary part which gives you the same semicircle for density of states. Now, consider this Q matrix as a saddle point solution plus some fluctuation. Then in terms of this fluctuation, the action will look like this. It will contain some quadratic and third order term. And already from this expansion, can estimate the characteristic width of a region near the edge of semicircle. There this cubic term is important. It gives you this. Now, I will not present here this instanton analysis. Just what it would be too long. But the whole result is the calculation of this Lifshitz tail of localized states. Now, let us consider again expansion of magnetization in terms of eigenfunctions, and we separate this spectrum of wave functions into two parts, which I will call slow with subscript lambda and fast with subscript alpha. Roughly speaking, slow are the guys who are living somewhere here, near this former age and localized states. And fast refers to the bulk of this spectrum. This expression you already have seen. Here this m with tilde corresponds to slow modes. Now, we are going to cool down our system so to decrease temperature, and here is tau
You need choke. It's inside the black. No, the black cup.
black cup. There are some pieces. So tau is T minus Tg minus 1. If we consider quadratic terms in the amplitudes, only quadratic terms, then this quadratic part of the functional will look like this. And epsilon is e minus 2, so positive epsilon means some eigenstates in the tail. If and tau naught c in power minus 2 third corresponds to this energy with epsilon naught, which I was also writing, epsilon naught of c minus over 3. Now, for any, if the store is positive but not very large, you always will have some eigenmodes with epsilon lambda larger than tau squared. So this mode will be unstable in linear approximation. Non-zero A is energetically favorable. It means that I need to consider higher terms. Let's write down full expression for free energy. Free energy as a sum over